So again, here we want to anti-differentiate this. Well, we can only anti-differentiate if we know the derivative. What gives us this derivative? Well, that's tan. So I'm going to get tan x. We know the derivative that gives us sine is cos. So we use negative cos. And we just use a plus c here then. Okay, so the antiderivative function looks like that. And this is called the indefinite integral. So what's some applications of this? Well, we're given the curve it passes through, so f of x, this is our f of x, and it passes through this point, so we're given a coordinate on that point, so we know exactly where it should be, and we're told the gradient function, well, that's gradient means slope, so that's our f prime function is 2x plus 5. So if I want to find f of x, I know f of x is related to the antiderivative of 2x plus 5 dx. Okay, so there's our f prime function. I anti-differentiate it to get that. So my f of x function, I'm going to get as x squared. Okay, it's going to be 2x squared divided by 2, so the 2's cancel out. 5x, and then we have a plus c. Now that plus c we can solve because we know a point on that graph. If I know a point on that graph, I can solve for an unknown constant. So if y is negative 1, x is 3, I know that c becomes the only variable, so I can solve for c. So this becomes 24, so c equals negative 25. So my f of x function is going to be x squared plus 5x minus 25. So that function will pass through that point, and its derivative will have this derivative here. Okay, looking at accelerations, whose derivative of velocity acceleration. So the acceleration's antiderivative must be velocity. The derivative of position or displacement is velocity. So the antiderivative of velocity should give me position. So it says here, we're given the acceleration and we need to get the velocity function. Well, we're going backwards of what we normally do. And we can say this, the velocity function is going to be the antiderivative of the acceleration function. And if we know the acceleration function and we know how to anti-differentiate that, yeah, I know how to anti-differentiate that. That's going to give me 6t squared over 2 plus c. So my velocity function ends up being 3t squared plus c. Well, I don't know plus c. However, I've been given a condition here that the velocity is 79 when t is 5. So formally stated, v of 5 equals 79. Well, I can plug the 5 seconds into my t, and the only thing left, the only unknown is c in that expression. So I can solve for c. So this is going to be 25 times 3 is 75. So I'm going to subtract 75 from both sides, and I get the c value is equal to 4. So now I can generalize this velocity function. v of t is equal to 3t squared plus 4. Okay, well that solves for that part, but the initial position is x equals 0 when t equals 0, and you need to find the position function. Here, the position function then, p of t, I'll call that, is going to be the antiderivative of velocity. Okay, so we're going to find that function. We're going to anti-differentiate 3t squared plus 4. So that power has to increase, so it's going to be 3t cubed, and I need to account for that cube power by dividing by 3. This is going to be 4t, and I can't forget the plus c. So there's my plus c. So there's my p of t function. I don't know plus c, but I've been given a condition, x is 0, y is 0, so p of 0 equals 0. That means if I plug in 0, I should get 0. So c in this case has to be equal to 0. So then finally I can write my p of t function. It's going to be t cubed plus 4t. We've worked out that c is 0, so that's my position function. And the final part of it is asks you find the position when t is 4. So I want to find p of 4. That's going to give me 4 cubed plus 4 times 4. That's going to be 64 plus 16. So 64 plus 16 is going to be 80 meters is my position in positive 80 meters.